Hey, welcome everybody to the Great Debate Community channel. This is Steve McRae, the host of the Great Debate Community, and well, I'm going to do something different here. We were talking about having different hangouts explaining to people mathematics, and I know a lot of people in our community are really good at them, really good at mathematics. We got EO, we got General Han Solo, there's quite a few, but I kind of wanted to see if I can actually remember what I learned about mathematics, what I learned about calculus, and be able to explain it to somebody still. A while back, I made a joke in the Great Debate Community that I thought was pretty funny, and a lot of people did too, including a friend of mine who's a PhD in mathematics, who teaches it in Cal State Long Beach. He is the professor, the head professor there for statistics and mathematics. And the joke was, what's the definition of insanity? Taking the differentiation of e to the x over and over again, expecting a different result. It's funny. People that want to link, you're gonna have to give out links to people, because I got so many different windows open right now, and I don't want to put the link out in the live chat. I don't want to.
Yeah, just tell them to message me.
All right, so just if you want to get in, just go ahead and message Dragnot, and he'll give you the link, and you can join. So, anyways, what we're gonna be doing today is I'm gonna be explaining to people the proof, or a proof, of why taking the derivative of e to the x is e to the x, and there's about at least 5 or 6 different ways of doing this. I think that each day I might actually do a different proof. One day use one way, one day use another way. Today I'm going to be using implicit differentiation, and then maybe tomorrow I'll use by substitution, or by Taylor series, which would be really interesting. I think that'd be a fun way to do a proof by using Taylor series. Unfortunately, I kind of have to remember how to use Taylor series, but I could do it. But anyways, this is going to be assuming that people do know a little bit about calculus. However, if you don't, that's fine. I hope people pick something up. And if you have any questions, ask in the live chat, or come on in and ask. I want to at least have it at some basal level that anybody who has never had math at least understands the concepts of what's going on. And then like I said, we have EO here, who actually teaches mathematics and is well familiar with it. And he's kind of going to back me up and point out when I make a mistake or something doesn't make sense. So let me screen share what we got here. Anybody any questions starting off? Are we good to go? Okay, guess not.
Let's do it.
By the way, we got Dragon and Odeon in here, so say hi, guys. And Midnight Sparkle.
There we go.
Hey guys.
Midnight soon.
I'm giving you guys mods. Can you show people as they come in?
Mm-hmm.
So I don't have to minimize my or expand my window. So maybe 1 sec. Everybody's gonna get mods. You get mods. You get mods. You get mods. All right. So show people as they come in. All right, so let me see if I can share my window here. Screen share. I'll be using OpenOffice Math Writer.
There we go.
All right. Now, can you guys see that?
Yep, I see it. I'm checking the
live
live
chat.
stream.
Please let me know. Okay.
OpenOffice. I gotta get this.
Yeah, this is a free software. Anybody can get this. It's called OpenOffice. It's by Apache, I believe. You can download it free. It's usable, it doesn't cost anything. It's got OpenOffice Math, OpenOffice Writer, OpenOffice Presentation. It's pretty handy. It's basically like Microsoft Works, only free.
Hey, Steve, I gotta ask, are you going to use f of x plus delta x minus?
No, I'm gonna explain the.
Oh, no, I don't mean today. I don't mean like another day.
Oh, I'm going to use a different way of proving this using the definition of the definition of a derivative, but that's a little bit more involved. So I'm going to do that one at some other point. But yeah.
I know that much.
Okay, so first we have to understand what a differentiation is. What are we doing when we take a derivative? Basically, a derivative is a time rate of change of something. It actually relates to the slope of a tangent line on the point of contact on a circle. Or if you have what's called a secant line is a line that goes across the circle and that has 2 points on it that touches the circle inside the circle. And then as that line moves towards the edge of the circle to become the tangent line, that decreasing value is basically what we're kind of looking at, the time rate of change until the point of where it actually is on that circle itself, and then we're taking the differentiation at that point, or the slope of the tangent line.
You mean to say curve, not circle? Curve.
Well, on a curve. Okay, but yeah, on a curve. But on a circle, you still you have on a circle. If you take a tangent line on a point of it, it's still the differentiation at that point, correct?
Sure, but so the secant line is roughly equivalent to a chord on a circle, but the problem is that some circles have, they have vertical tangent lines where there's no derivative. But yeah,
so there'd be you can't take the derivative of a vertical line because it's indeterminate, right?
Yes, go ahead. Sorry.
Correct? Yeah. Okay, so you're right. So anytime a curve, this works not just for circles, but any curve, if you have a function and you try to take a line that's a tangential line to that function, that point of intersection, that's what we're taking the derivative of. So it's basically the time rate of change, how fast something is changing with respect to something else. So the nomenclature I'm going to be using is this Leibniz notation. The other notation would be Newton's notation, where you have like f of x prime as a differential, or excuse me, as a differentiation. I could use that notation too, but I don't like it. I don't think it explains things as well because it doesn't show you visually. And that's just my personal preference, however. But if you see something written like this, it's going to be written as f of x prime equals, and this is the same thing as saying df of x. Okay, I know, yeah, you hate it written that way, don't you? Let's try this. There we go. Same thing as saying that, correct, Dio?
So you want to change that x in the numerator to a y, but yes.
Yeah, you're right. dx dy. There we go. dy dx.
Yeah, and you don't need the parentheses there.
I know, but it's just it's clarification purposes. See, the one thing about math is that there's a lot of different ways you can format stuff. Like this is exactly the same as saying this, or you can say it this way too.
And forgive me for being pedantic, Steve, but your prime should go after the f, not afterwards.
Okay, you're right. Well, I've seen it written both ways. But you're right.
But I don't know. It's usually f prime. Yeah, that's
f double prime. Yeah.
By the way, we got 6 viewers, and I'm the only one who commented in the chat. So I'm guessing not a lot of people like this subject.
Yeah. Well,
I know I do.
We'll see. I would assume, though, if they're having a difficulty, somebody's going to mention it because you can see in the outside chat the feed, right?
Yeah.
Okay, so this would be a first derivative. You're right. This would be the second derivative. Or actually, I guess you would write it like that. No, I guess you can't write it like that in Math Writer. You have to write it like that. 2 prime. But anyways, we're not going to be using that notation because, well, like I said, I'm not a big fan of it. But
no, and you're absolutely right. When they teach students implicit differentiation using the chain rule, it's always best to use Leibnizian notation because you can see it helps students see as a heuristic. It looks like stuff is canceling out, even though it's not strictly speaking algebraic cancellation. But
that's right. What I think too. I agree. That's why I particularly like it. And you're right. It's not canceling out like an algebraic equation, but it just kind of makes a little more sense intuitively, I guess.
Yeah. So, I tried doing some implicit because like math. I don't know if you noticed math. There's a website called Math is Fun. They have a calculus section, and the implicit section of it, finding the derivative implicitly, kind of well, I had a little trouble with it.
Well, let's see if we can help you out with this one. Okay, so the question is, why does d over dx, e to the x equal e to the x? Why is it I'm taking a derivative of that? Why does it actually produce the function? Okay. Normally, when you take a derivative of something, it's going to give you, so for example, if I take a derivative of x squared, we've talked about it before, the derivative of x squared is 2x, right? So, and 2x is obviously not the same as x squared. So in this particular case, taking the derivative gives you the original function, which is kind of unusual, but it's an integral part of math why this is. It's actually very important why this is actually the case. So let's see if we can actually prove it. So we're going to start. The way this works is I type down here in a special little language that OpenOffice uses, and then it'll show up in the top. So kind of look to the top there because I got to do this the right way to make it formatted right. So e to the x. So the first thing we're going to do is we're going to make an assumption. Oops.
Oh, God. I'm not ready for this. Sorry, I was. Sorry to interrupt.
Yeah.
You'll be fine, Midnight. You're in good hands.
Okay. So, I got to make sure. Okay. Okay. So the first assumption we're going to make is that e to the x is going to equal to y. So we're going to arbitrarily just pick a variable. I like y because it actually makes sense, and y is usually the independent variable. or should be the dependent variable. So in this particular case, e to the x equals y is the assumption we're going to make. And you also might see it written like this: expx equals y. All that means is the base is e. A lot of times in formulas, you see it written as exp because of formatting issues, or they don't want to write a superscript. A lot of different reasons why. If you have a big formula in brackets, it's very hard to do superscript sometimes. So if you see something like exp to the x, don't freak out. It's nothing magical. It just put the base as e. So it just means e to the x equals y. Okay. So we're just going to make that assumption, e to the x equals y. And so we go to the new line. You're with me so far then, Midnight? We're just going to say e to the x equals y, okay?
Yes.
Okay. All right. So we're going to go to 2.
You're taking the natural log of e to the x.
Yeah, and I'm going to show you something interesting here in a second here. Okay. Oop, that's supposed to be D arrow, double arrow. There we go. Got to speak the language it knows. In mathematics, there's different types of logarithms that we all know, right? In most of the time, like in Wolfram-Alpha, logarithm base e is the same as ln. So just by saying log, if you go to Wolfram-Alpha and you type in log, it's going to assume you mean the natural logarithm, not base 10, because we all grew up in school learning logarithm is base 10, right? Log meant base 10. Well, in higher maths, that doesn't really hold true. So if you see log, you got to know if it means natural logarithm or logarithm base 10, but Wolfram-Alpha and most proofs nowadays will use log to mean ln. And EO maybe can explain the reasoning behind that. I don't know why. I think it's confusing.
No, you're exactly right. The higher you go in mathematics, you're exactly right. exp means e to the x, and log means log base e, or ln. I just want to point out, implicit in our entire discussion here today is the fact that the inverse of e to the x is in fact ln x, or in your notation, the inverse of xp of x is log x.
Yeah, and yeah, exactly, because I'm gonna be pointing that out here, actually.
There's a few people watching, so it's uncommon to get to do any type of differentiation and get the same thing. It's like, it's one of those odd things. So for those of you who are just watching, there's a joke attached to this and this funny phenomenon. So that's what is going to be demonstrated here as to why, because I learned this as a convention. It is, if you need to take the derivative of e to the x, it's just going to be e to the x. A proof was shown, but I honestly didn't pay too much attention to it. I just accepted it and moved the fuck on. So
yeah, it's funny you mentioned that. It's true. It's sometimes when you take some classes, they'll just tell you that the differentiation of e to the x, e to the x, but they're not going to tell you why. Maybe you're not up to the level to understand the proof. This is not a difficult proof, but there are other times in mathematics where they'll say just accept this and go by faith, even though people say, we don't use faith in science and math. It's true, you don't, but you gotta have faith in your instructor that they're not trying to mislead you. But you may not be at that level to understand the proof. Like in nuke school, there's a lot of times at the beginning they would tell us, hey, look at, you just accept this as is, and then we'll explain it to you later on, like months down the line when you understand a little bit better, right? So.
And let me support Steve here by saying how important this is. This formula comes up, this is the most important function in mathematics. It comes up in finance, nuclear decay rates, cooling, heating, you name it.
Compound interest.
Steve could explain, that's right. Steve could explain better than I can all the physics applications, but this is literally the most important function in mathematics, so it's well worth the time, Steve.
Anybody that's physics or biology would know this, because bacterial growth rates are contingent upon this.
Sure enough is. I've calculated.
Decay is completely because of the formula. The same thing for compound interest. P per PERT, if you guys remember, P equals ERT, where you have your initial condition plus your rate of change times your time as the exponent of E, and then you can figure out how much of material you've lost, how much nucleotide you've lost. So yeah, these things come up all over the place. They're ubiquitous in physics and math and biology. So in the second part of the proof, we're going to take the natural logarithm of both sides of that equation of e to the x equals y. Okay, so e to the x equals y. We take the natural log of both sides. We end up with natural log e to the x equals natural log of y. That'll give us x equals ln y. Now we're going to show why that gives you x equals ln y. Okay, so this is going to go back to what EO was saying here about the logs, and I think Dragnet was mentioned too. You guys see this as I'm typing? I'm kind of looking over my notes here.
Yeah, take your time. I mean, as you do that, I can fill in the dead space. If you guys want to learn some calculus, I mean, that's something we can add to the great debate community. Becoming more, mathematically literate will in turn help you become more literate in biology and physics and some of the other areas that we've mentioned. And as someone mentioned in the chat, computer science is another area. I remember speaking to Scott Geerton as I was doing implicit differentiation and lamenting as to, how kind of difficult it is learning different techniques and then trying out each one to see which better fits my style of learning. And, he also, remember how difficult it was while he was taking calculus and getting his degree and trying to learn this particular aspect of calculus. So it does take some people longer than others. Like math, I do enjoy doing math, oddly enough, but it's not something that I would do as a passion, unfortunately.
Yeah, one size does not fit all. And like you said, each proof is a little bit different, and they all, like EO had pointed out earlier, this proof does make certain assumptions that I'm not actually showing. Right? It does actually show them that you can actually differentiate this. But so, that is a little more involved that I didn't really need to get into.
When you did log base e, log base ey to the y equals x, are you taking, was that the property? Is that the
log base
law
e
of logarithms?
Well, log base e is exactly the same thing as a natural logarithm. So all I did was I changed ln to log e.
Okay, because I was trying to figure out did you use a law of logarithms in order to do that?
The second part is, so let me explain.
Second part is, okay, all right.
So when I say ln e to the x, okay, I'm actually saying log e y, because y is equal to ex here, right? So this is the exact same thing on this side of the equation.
Yeah.
Okay, on this side of the equation, x is going to equal to ln y. But hang on. Well, actually, let me. I'm jumping again here. Let me explain why this actually works first. The log base e of the y is the same thing as taking a ratio of the natural logarithm of y over the base. Okay, same exact thing. So when I have, let me go back down to here. When I have that ln y over ln e, I'm going to end up with ln e. Oops. Let's see here. ln y over ln. Explain why this works. ln y. You're not seeing that. There you go. Keep on forgetting how you got to scroll down here.
EO, can you see the side chat?
Let me see if I can make this smaller so I can scroll down a little bit more. Tell me if you guys can still see that. I just made it smaller so it's easier to read.
No, Drag, text me on your phone. I can't see it.
Okay. Well, I was going to say, what law of logarithm is he? What specific law is he using? Because I was going to.
It's called a change of base. He's simply just changing, showing change of base. Yeah.
Okay. I want to show people exactly what, instead of just deferring to it, just kind of quickly show people to give them a visual aid.
Okay.
Oh, and Steve, next break I have some filler if you need it.
Okay, no problem. I just when I'm typing here. But for example, okay, so right here, this change of base, the ln y to ln e, is going to be equal to ln y. Okay, and the reason for that is very simple. Ln e is equal to 1, and that's the case. Then ln e equal 1x equals x. Okay. Are you presenting, or am I presenting still?
Oh, there we go. No, I as you were typing, I'm just showing people. What I was talking about here, what Steve did, and when he produced the log base, log base e to what is it over here? Log base e to the y. Yeah, the change in base. This is what we were talking about there. So that's just a property of logarithms that you can use to change them around. So
correct.
yeah. All right. Let me.
Yep.
Go ahead.
Okay. So percent. All right. So because ln e equals 1 and ln e x equals 1x equals x. So basically, because ln e is equal to 1, 1x is equal to x. So basically, on this side of the equation, I'm ending up with x. And on this side of the equation, I have ln y, which is exactly what we have to begin with. X equals ln y right here. Okay, so I'm not really changing anything. I'm only showing you why this actually works out. X equals ln y, because on this side of the equation, I have ln y, which is equal to this, which is equal to this, which is equal to this. This is what the great thing about math is. You want to keep an equality across the equal sign. Now, one mistake that I've noticed with people, they think that the equal sign means that everything is perfectly equal with each other, all as far as properties. It doesn't really mean that. It just means there's an equivalency. Okay, and once you get into a little higher math, you learn something like called the equivalency principle of fractions, and how fractions are actually defined in rings and groups and fields and shit. And it's kind of really interesting because it really explains to you that this equal sign does not mean all properties are the same. Because if I was the truth, if I said like x equals y, x and y are different symbols. They might be the same in value. There's equivalency there, but they do not mean that they're exactly the same thing as far as all properties, including the symbols used, right? So it's good to keep in mind when you start learning about how things are defined as fractions in what is it, in a field? I think it's defined in a field, not the ring. Is it right, EO?
No, you're right. The first time, the ring. To your point, Steve,
okay, to the ring. Okay.
The German mathematician who first used these symbols, you'll notice the equals actually is just two parallel lines. And he said, what could be more equal than two parallel lines? So that supports your point. It's a parallel.
There you go.
If you like.
Yeah, I like the way, I didn't know that. That actually makes a lot of sense, actually.
Well, where we're at right here, Midnight, was there something that you wanted to kind of ask about real quick?
Well, okay, assume that ex equals y, or x, let's see, log, since log e of x, y, I mean, I don't even know, I wouldn't even know what to ask.
General, get General in here, please. He wants to join.
Yep. Oh, I'm sorry. Did he send me a message on this fucking screen?
I sent it to him on the outside chat.
Oh,
but
I'll get him in here.
Okay.
So are you, well, I want to make sure, because it's one of the interesting things about trying to teach someone, especially with math, you can't just kind of gloss over some of the parts and think they're, I guess, not as important, and just understand the rest. It does build upon itself, because some of the same techniques that we'll be using in the beginning of the problem, you'll be continuously using throughout the problem, especially when you get into using doing what's it called, differentiation.
Learning math is like building a house. You need a solid foundation, don't you?
Oh yeah.
I mean,
yes.
And even in the problem itself, like in a proof like this, you constantly have to reference back to certain things. Can you show him? For example, like the next step,
yep.
all I'm doing is taking the differentiation of both sides of this equation here, which where we started with, x equals ln y. It goes right back to where we started. So I have ln x on this side, I have x on this side, same equation, but now I'm going to take the derivative of each side. So you guys see that, because the d over dx, right? And I can write it two different ways. I can write it like this, or I can write it like this if you prefer. It makes no difference. It's just format. But if it helps you to understand it, you can actually write it this way. I prefer it this way because this is easier to visualize.
Yeah.
Actually, I missed an X here. I would have to add an X.
Hello, General.
There we go.
Hey, guys.
So I mean, EO, do you prefer it written this way, or do you like using other notation? I'm just curious.
So what have you discussed with us, Steve?
The first, you want me to go over the steps again real quick?
Well, yeah, it might be better for me and everyone else, especially me.
All right, let's okay. Well, yeah, I don't want to lose people, so we don't mind a little recap. So we're going to explain using implicit differentiation why taking the derivative of e to the x is equal to e to the x, and there's a lot of different proofs to do it. I took a lot of different types of proofs. I slummed them together, and then I wrote my own explanations of it, because I noticed in proofs they don't really explain it. They just, you know, go from one step to another, but they don't explain each step. So what I wanted to do was explain each step, and then in the next session, I'm going to use a different way of proving it.
Would you like me to show that you can do it in 3 lines?
No, I know how to do it in 3 lines. That's not the point.
Okay.
No, this is actually to show that there's different ways of doing it, and I want to be able to show myself as a layperson can actually do this, not somebody who actually teaches this stuff like you or EO. I wanted to show that anybody can learn how to do this, even a layperson might like myself that hasn't had calculus in 25 years.
You and I will become best friends.
So, anyways, I start off with the assumption that e to the x equals y, or the exp equals x over y. I then take the natural logarithm of both sides, right? And then that's going to give you x equals ln, which I'm taking the derivative right now. That's where we're at, General.
Okay. I see.
Okay.
Right.
Nice. So let's take the derivative of both sides now. This is where the fun comes in, guys. Because Dragnut, can you guess what we think we're going to be able to use now?
What they're going to be able to use?
What rule do you think we're going to have to be using now to actually kind of continue to figure out how to do this?
That's probably another fucking law of logarithm.
Yeah, it's not a logarithm, but it is a very popular rule.
ddx of ln y.
Oh, the fucking chain rule. Are you serious? I quit.
Because of the chain. Oh, I didn't spell the cares right. Hang on. Okay. So yeah, we're going to be using I'm going to be using now. You don't have, again, there's different ways of doing this, but again, I think that this way explains it the best. And I'm just going to go that route. So first, let's explain what the chain rule is for everybody. So the chain rule is basically how you differentiate between 2 sides of an equation when you have different variables involved. So the way it actually looks like is this. Let me get to my chain rule here. So you may have seen it written in many different ways. There's no one size fits all on this. So if you've seen it written different, it's not that one is better than the other. It's just there's different ways to write this. Okay, so why is it cutting off like that? There we go. All right, so this is one way to write the chain rule, and you might see it as dx or dz over dx equals dz over dy, dy over dx. That's fine. It's basically just a way to describe how to take a differentiation on one side with respect to one variable while holding another one constant. Would that be a best way to explain it, General, you think?
Yep, that's it.
Okay. So this is what it looks like written out as far as the chain rule. Again, you might see there's many different ways you can write this, not just using this notation. You can write it using Newton notation. You can write it using quite a few different ways.
This is Leibniz notation.
This is Leibniz, yeah. I prefer Leibniz. But if you want to use Newton notation, again, I haven't looked at this one, but I think the Leibniz notation would be.
This is Leibniz. So
I mean, not Leibniz. I mean Newton.
Yeah, if you choose Newton, you put a dot.
If I may, Steve, can I just explain for the chat and why we even have to do this? So on the right-hand side, which, everyone knows the derivative of x is 1. It's, it's for every change for every unit of rise, there's 1 unit of run. That's fine. We can actually just use high school math for that. The problem on the left-hand side is we have a function y. It's implicit. We don't know what x is. Why? So we have an implicit function of x, and that's why we have to use the chain rule here, folks, because we don't know what y represents. Y could literally be anything. All we have here is ln of y. So y itself is a function of x, and that's why we have to bring in the chain rule.
Okay, so let's explain how this is going to work when we actually do the chain rule. So we're going to take the derivative of both sides. The equation is still ln y equals x. Same thing as x ln y. It's just written on the x on the right-hand side rather than left. So you got to remember that ln y equals x is exactly the same thing as x equals ln y, okay? So I'm taking the derivative of both sides of this particular thing. This is going to give me this. And the reason it gives me this is basically this takes the place, this just fits up here in the numerator, okay? So you actually end up with d ln y with respect to y, dy dx equals dy dx with respect to x. This is where it gets really complicated, because the derivative for ln y over dx is going to eventually give you 1 over x. I'm going to explain to you why. This part of this term right here stays as is, and then this is actually going to go to 1.
You know, I gotta say, I gotta say that the way the chain rule is set up always confused me. You know, the one on top is it always confused me.
Right, I
could never figure it out. Yeah, the top one.
Again, like, this is going to be the left-hand side of the equation, right? So I'm just taking the derivative of what's on the left-hand side of the equation. So let's parse it out. I'm going to do a little bit different than when I wrote it, so I explain it. This left-hand side of the equation right here, dy dx over ln y, that's going to actually become this. So let me show you. Over y times dy dx. Okay. It's going to, you know what? Let me use over. Sorry. Okay. This right here is this whole thing over here is going to look like this. And then it's going to end up with dy dx. I keep doing this wrong. Over dx x, which is the same thing as saying dx over dx will equal to 1. I'm trying to think of the easiest way to understand to explain this. This is kind of the hardest part to explain here. Maybe EO, can you explain the chain rule a little bit better than I can? So hold on. I get the concepts, but it's really hard to explain.
So let's go back to the step. You don't need the extra y on the right-hand side. In fact, it's just obfuscating things. You see where you have dy dx times x?
dy. Okay. Here's the chain rule. What section? 1, 2, or 3?
So in the second step there, you need to remove the y on both
right
sides.
Here. Get rid of that.
Yeah, on both sides.
Yeah, I got
so
you.
So it's d of 0. Okay, still with me?
Yeah. 1 second.
And
then, well, I got it. I know what you're talking about. Okay, so it'll look like that.
You could put parentheses on the LOY. It's fine if you don't want to. So you're perfect until the next step where you need to remove the dy again from the right-hand side. You see that?
dy. Oh, yeah.
On the right-hand side. Yes. Okay.
Okay.
So, you're doing fine. You don't need any help. I'll just state again, the reason we have to do this, folks, is we know what the derivative of natural logarithm. If it had been ln x, we know the derivative is 1 over x. The problem is we don't know what y is. Y is some implicit function of x, and that's why we have the chain. The chain represented by dy dx on the left-hand side, the second term, represents the fact that we don't know what y is. And so we have to account for that, and that's why we're writing y dy dx.
Perfect. And you know what? It's easy to explain after that. That clarifies it a lot, I think, for people. The derivative ln x, this is something you just kind of have to know. The derivative of ln x is equal to 1 over ln y is 1 over y. Okay. The reason for that is because the integral of 1 over x is actually is equal to ln x plus a constant. So the derivative is just the opposite of an integral. So this is kind of one of those rules you kind of just have to know. I don't know of any real way of explaining that other than you just have to memorize that one. Unless, EO, do you have a better way? Because this is something that you just have to memorize, that the natural logarithm of x is going to be 1 over x. Therefore, the natural logarithm of y is equal to 1 over y.
And you're fine. The only thing I want to add now is everyone notice on the right-hand side, we have an explicit function of x, namely x. Y equals x. That's explicit. We know what it is. Just like everyday English. Explicit means we can clearly understand and explain it. On the left-hand side, we have something hidden. It's implicit. And that's why we have to go to this extra trouble. Sorry, Stu, go ahead.
Right. Exactly. Okay, so what I'm going to end up with, taking the derivative of this, which is 1 over y. Again, something you just have to, This right here, I don't know what it is. I mean, as far as it being implicit. So I'm just going to leave it dy dx. And on this side, d over dx with respect to x is taking the derivative of x. The derivative of x is 1. Okay. Again, you kind of have to know how to take a derivative to understand this. But the derivative of any variable that's a single variable is 1. So the derivative of y is 1. Derivative with respect to y is 1. So then I end up with okay, so since the derivative of ln y is equal to 1, right? And I'm going to just copy and paste this rather than trying to rewrite it. since the derivative of L and Y equals 1 over Y, and the derivative, the 1 over Y dy dx is equal to the derivative of X, and X is equal, the derivative of X is 1, I end up with 1 over X, dy over dx is equal to 1. Okay? Does everybody see how you get that? Because the derivative here of this term is 1 over X. This I'm not taking any derivative of. It's just dy dx. And this term on the right-hand side, the derivative of X is 1. So I end up with 1 over Y, dy over X, dx is equal to 1. Everybody get that so far? We good, Midnight?
Let's see.
Well, you know, I stepped away to throw out the trash, so yeah. I mean,
I'm gonna stop typing this. I'm gonna do it all at once. There you go. We're gonna scroll down. I was typing this as we go, but I'm just gonna copy it all over and then do it as we go. Okay, so now I've got this so far in the proof. 1 over Y, dy over dx equals 1. Now, all I have to do now is multiply each side by Y. So if I multiply each side by Y, right, I end up, you know what, I'm gonna change this to over, because again, I think it looks better.
So you should just have what, dy dx, because if you divide both sides by 1, because that 1 times 1 over Y, the two Y's would cancel out, would they not?
Where, right here?
Yeah, if you multiply.
Yeah, right here. That's what I'm trying to do.
Y.
I'm gonna times each side by Y. That cancels out this Y. Okay, just leaving me Y, and leaving me a D. Man, let's see, a D over dx.
You're fine, Steve. You're missing a Y on the on number 4, so you want to write Y equals dy dx.
Dy dx. There we go.
And for those watching in the chat, he just switched the sides, but it's fine.
Okay, so okay, so if I times each side by Y, and then I substitute ex for Y, okay, Y equals ex, then I end up with ex equals d over dx equals e to the x. Okay, so all I'm doing is I'm taking this equation here, and I'm multiplying both sides by Y. The Y's cancel out. Okay, and I have Y on this side, and I'm just putting ex in place of Y. I'm substituting ex for Y. So now that is going to give me ex equals d over dx equals e to the x, which exactly is what we're trying to prove.
Because we did a substitute at the beginning saying that for every Y, or excuse me, so every time you see Y, that's actually a substitution for e to the x.
Right. My very first assumption. That's why I can substitute it back in later on, because I made that assumption initially that when you see Y, I can put in e to the x. And I wanted to real quickly to show why that breaks down the way it does before. When I times Y on both sides, I end up with Y on this side. This collapses, and I end up with just dy dx, so Y equals dy dx, which is what I have here. Substitution ex back in, I end up with ex equals d over dx equals e to the x. Therefore, e to the x over dx equals x, e to the x QED, which is exactly what I was trying to prove from the very beginning.
So, sorry to steal your thunder. What you've exactly shown is that the function y equals e to the x is its own derivative.
The derivative of the function is its own derivative. Now, again, not the best explanation. I haven't done this shit in 25 years. I'm just happy that I can actually explain it at all. I don't have to be effectively great at it because I'm not a calculus teacher. Please don't think that I am remotely qualified to be doing this, because I'm not. But I have had calculus, but at least I'm happy that I remember enough to go, oh, you know what? Yeah, I understand this. I do remember it. I can do this. Because I tell you what, I would love for any member, pick one, of the Clown Car Posse to do the next one and do any proof they want and explain why e to the x equals the derivative of e to the x using any proof they want. They can use the Taylor series. They can use, you name it. They can use. They can do it.
You know, I don't think. Go ahead. Sorry.
For the sake of the audience, do a really simple one, like the basic one that's taught in freshman calculus.
Okay, 1 sec. Hang on.
Don't need to tell you what to write.
Invite Edgar, and you can do. We can do expert.
Yeah, invite Edgar.
No,
you did not.
I invited him.
Yeah, he did invite.
Did you really?
That's why it's fine. Yeah, this is why I said, Mr. ID, this should be good, and he didn't join yet.
I mean, we could give him a simple one like, I don't know, 2x.
Yeah, we did.
Okay. No. You gave him x
gave him a
squared.
tricky one. You gave him x squared.
Oh, did I? Oh, 2x is just x.
I know.
Okay. So let me see if I can. I don't want to start.
Well,
I don't want to.
I mean, I'm not trying to brag here, but I sent General some some interesting things, and hopefully maybe he'll comment on them.
Okay, let me see. E to the x. Let me see if I can do this in like much shorter. Equals y. Okay, so that was my assumption. I take y equals x. Let me think here. Oh, let me make a new line here. Am I on the right track here, General? And just like three lines.
No, I'm typing in the side chat.
Well, I've used. Let's see here. I'm trying to something else. So I'm using a prime notation. So I'm not looking at the side there.
So really is simple.
Y prime equals y. So d x e to the x equals e.
Wow, General.
Something like that, General.
No. So right.
That's pretty compact way of doing it.
Well, actually, his way is better.
You need a space between the x and the 1 over y times y prime, Steve. But yeah.
So I just start with ln of e to the x. The natural log and e they cancel out, and so it's x, right? So then you take differentiation of both sides, d dx of ln e to the x and d dx of x, and we know that the natural the differentiation of a natural log is 1 on, so it'll be 1 on e to the x. But then you're wanting to figure out what e to the x is when it's derived, so that's why you leave d dx as e to the x by itself. So if x is 1, multiply the denominator e to the x into 1, and lo and behold, you have d dx e to the x equals e to the x. And so that's the answer.
Now now using a Taylor series.
And yeah, you could do it that way, which is a lot.
Well, I'm going to be doing that one. I don't think I'm going to do that next time. I'm going to be doing that.
I don't even know if what I said translated to the screen, but yeah.
I'm seeing if I can do this way.
So Steve, when you get a blank page, I'll show you something really cool about this whole process.
You want a blank page?
So what's really cool about math is that one man's definition is another man's theorem, or woman. What's really interesting is start off with just write dy dx equals y. Sorry, no, dy dx equals y. You need a y on the left-hand side. Okay, so what's really cool is you can start off discussing E by saying, I want to look at the solution to this equation, and you can have a full discussion of E. So you can go backwards if you follow what I'm saying. So you can start at your conclusion and then work backwards and talk about the function y equals e to the x. It's pretty cool. And we actually did that in Calc 2. Right, and so that's how, and what you'll find with some really sophisticated textbooks, we can use these same techniques to talk about the derivatives of sine and cosine. And you can start off with, okay, sine and cosine are going to be the specific solutions to these fourth order ordinary differential equations, which aren't, it sounds, folks in the chat, it sounds tricky, but it's nothing really more complicated than what we just did.
Ah, there's a sigma.
Is this the right one? Is this for the Taylor series? Am I remembering? See, I haven't figured out how to use this program too much yet, so my nomenclature is off. Let's try that. Is that right? So let's see. I remember correctly, e to the x is summation of x to the n divided by n factorial. I think that's right.
Yep.
And then you can use that for the Taylor series. Now, I think on this one you could write it as. Is that right? So. If people want to know what a summation is, that little, you guys want to continue on with a little more math stuff, or do you want to like start a new thing?
Sigma bad.
Sigma's not that complicated. All Sigma's saying is summations. So if I have some, let's say x going from x equals 1 to 2. Let me get rid of this top thing here. I haven't looked at this in a while, so hopefully this is right. And let me add a new line here. One thing I don't like with this program, you got to type in new line every time you want a freaking new line. All right. No, one. How do you write the summation on Writer? You guys know? Oh, well, you know what? I think I do know how to do it. I think you do it this way. Sum x equals 1 to 2. Is that how you do it? No. Do you guys use Writer? I don't. Normally you'll see like underneath the sum you'll see like x equals 1, and then the top you'll see like the 2.
Oh,
so.
You're talking about like when you're doing like when you're arranging limits.
The indices of summation. Yeah. So
yeah, the indices. How do I in Writer? How do I put the indices in correct form for the summer end?
No idea, mate.
In
general leftist.
That's I know what you're talking about. Honestly, I'm not like I don't know what coding language that they're using. So,
well, let me see if I can do it. Let me just see if I can kind of fudge it a little bit. X equals 1. New line. I'll see if I can fudge this a little bit. Okay.
Oh, general left.
And then I'll put this above here and equals.
He's coming back.
Okay. New line. I'm just really fudging this. Okay, that's the best I'm going to get it. Does that look a little better?
It does, Steve. But again, so you're going to hate me, Steve. But you don't need the n equals on the top.
I know at the top.
The 2 will suffice.
I know. Okay, so.
So what is the n denoting?
Okay, so the n is your natural integers. Okay, your natural numbers. So it's just saying that you're going to take the first step, which is going to be we'll do this in order so we make sure we get this right. So basically, you stick 1 in there. So you have 1. Okay, plus then you stick 2 in there. Okay, 2 equal. So you have 1 plus 2 equals 3. So the summation of n to the 1 to 2 of x is 3. Does it make sense?
Me, Steve. It does. Forgive me, Steve. But if you're going to do this as simple addition, you don't have x there. You have n. N is also the variable.
Oh, you're right. All right. So how about?
Otherwise, we're talking about power
how about
series.
we just do it that way?
Yeah.
Yeah. I can do power series as well, but let's just keep it simple right now.
You know, couldn't you do
power
limit
as
x?
Have like x to the n.
Couldn't you do limit as x approaches infinity?
I'm not taking any limits. This is not a limit. This is a simple sequence. I mean, in fact, let's just start off even simpler than this. Let's just say sum of 3.
You have an x2, which
new line. Let me get some new lines in here.
No one be scared.
Okay.
All Steve is doing is grade 3 math in a different language.
Yeah, this is like really, really simple. This is just simple. It just looks confusing, but it's not. So if I say sum 3 drag, what do you think the solution is for that? It's not being complex. I'm just saying 3 plus nothing. Is Dragon here?
Here you go. I had to walk to the trash can real quick.
If I just saying what's the summation of 3 and I don't add anything to it, what do I end up with?
Should be just 3 if there's
should be just 3. So the sum of 3 is 3. Okay. So
I've not actually done Taylor series, but I'm somewhat familiar with the concept.
This is not Taylor series.
Are you just using some the sigma as an operator?
This is just doing summations.
Okay.
Yeah. But unfortunately,
to be fair to Drag Steve, if anyone who's taking calculus sees that, they'll assume it means from 0 to infinity without the indices.
That's true. Okay, so what he's saying is the indices is what I'm taking it from. So if I say x equals 0, and I have an infinity up here, see, I don't know how to format these things properly. Well, you know what? Let me try new line here. New line. See if I can add some padding here.
Steve, when you upload this, can I make a humble suggestion? Cut it off at the derivative part because you did a good job. Because now we're just kind of fooling around. Just my humble suggestion.
Sure.
Oh, first allow me to download the entire entire stream.
Well, you know, I mean, it doesn't matter. If people watch this entirely, it's okay. I'm not doing this for like a YouTube thing where people can come here and let's see how they actually do this right. This is just for our own edification kind of stuff.
Yeah.
So,
So,
I guess
I mean, we could just put timestamps in there. To be fair, we'll put timestamps in. Here's where it begins. Here's where we start talking about summations, and so people can kind of click through and see what they want. But that's after the fact. But
yeah. By the way, this actually worked out okay. What EO is saying is that without any indices, it's going to assume 0 to infinity. Okay, but it doesn't really matter since 3 doesn't have any variable with it. It doesn't matter what the indices are, right? The summation of 3 is 3, regardless of whatever I'm taking the indices to be. N could be equal to 0, N could be equal to 1, N could be equal to 1,000, N could be equal to 1,000,000. The summation of 3 is still 3. Does that make sense, Midnight and Drag?
let me see.
Yes, sort of.
Okay, think about it. I'm only taking the summation of what I have. I have 3 apples. How many apples do I have?
Oh, you have 3. Okay, no, I was
That's it.
looking because I'm not used to seeing this notation. Yeah.
So whatever my indices are, it makes no difference. Whenever I haven't had a variable in there yet. So now when I have a variable in there, which is I'm going to be doing here, okay, and let me.
I'm sorry, Steve, but you invited me. No, that sum is 3 times infinity. Whenever it just repeats 3, each time it's 3, right? So you're adding it. So it's 3 plus 3 plus 3. You don't need the variable there.
No, you do need a variable there.
No, think about it. Each time, what does that mean? It's not changing, so it's the constant 3, and you're adding it infinitely many times. Bring general back if you need to, but that's the problem. What you've done there is now you're adding 3 infinitely many times. Yeah. The only way what you're saying
you're right. If
you go from 0 to 1, or be careful.
All right, so let me actually put it in proper notation. Then, yeah, you're right. So let me do it this way. So if I do it this way, does this make more sense? Then
if you go from 0 to 0, then you're right. It is 3. If you go from 0 to 1, then you get 6.
Let me do it this way. Okay, you're right. Because the indices wouldn't matter. I agree with you. All right, so there we go. That's the same thing.
Yes.
So the above the sigma is that your lower limit, and then below it's your upper limit as to how many times? Huh?
The other way around.
Okay, it's the other way around. Okay.
You want to go from lower on the bottom to higher on the top. All right.
So does everyone get that? We're adding 3 exactly 1 time. Sigma just means sum, the Greek letter for S.
Right.
Right, and since there's no variables in there, all you have is 3. So there's
right.
So
each time you do an indices, you just do 3. Right. Yeah. You know what? It's been so long, but you're right. If I have if I have indices in there, if I said I go 0 to 1, that means literally I'm taking 3 and I'm just taking 3 again.
Yeah, I've used these before. I just haven't used them in a while. I mean, yeah, there's a lot of stuff I don't remember.
Now I got to format this one right. So sum of n. No, that's not going to do. How do I get this one?
Eric's saying, hold on. Eric W saying actually, it's not 0 to 1. It's 1 lower, 1 upper. And then he has a little cute face thingy.
Oh,
it's fine. You can.
I don't think it measures either way.
Fine. You can begin at 0. He's wrong. It's the same as going from 0
to
1 or 1 to 2
your indices begin,
3 to 4.
Yeah, you just do an indices.
You can begin anywhere.
Yeah,
we can go from 1 billion to 1 billion and 1.
Right. But if I have n equals 2 on the bottom and 2 on the top, it's still 1 time, right?
Exactly, Steve. Yes.
Yeah. Yeah. I mean, I remember when you're doing series, you can do an indices shift. But here, you're all you're doing is you're saying that you're taking 1 of the 3s from n to 1 to 1 is only 1, so you're only taking 3. So if I have n to 2 to 2, it's still 3. If I have n to 3 to 3, I can start the indices from any position I want. Correct?
Yeah, and let me make a tie into the Kalam cosmological argument. We can go from minus infinity in the bottom to 0 at the top to talk about infinite regress.
Right, and that would be like this. We could say negative infinity, or maybe that would be positive infinity. So let me see here. So that would look like this if we're talking about negative infinity to infinity. So it would look more like that.
Oh,
And
Steve, that would be really cool if you want to do next time. You can prove that 1 + 1/2 + 1/4, etc. = 2.
Oh, I can get that
next.
in there. Yeah, sure, I can do that one. But I'm just trying to get this formatting right. So let me get rid of this because you got that down.
No, if we're doing it, we'll do Newton's law of cooling and finds out how long it takes for
Newton's law of
true
cooling.
empiricism's ears to cool down once he gets pissed off.
Newton's law of cooling deals with how fast things are going to cool down with different types of materials and the thickness.
But Stephen Drake, let me give
capacity.
you did an example. The equation for that is y prime equals minus ky plus the constant of the room temperature, and that's so cool because it's exactly related to what we were just talking about.
But Dragna, where have you heard that term before? The Newton's law.
Oh, Newton's law of cooling. Oh no, yeah. The fuck was that? I don't know.
He invented it.
It's funny you just talking about. I talked about that with General the other day.
I know.
No, I got Newton's law of cooling from my calculus book because we were calculating. We were doing fucking. It was something. The applications of calculus, and so that was one of the many chapters in there was Newton's law of cooling, and you could determine how long your drink would get to the same temperature of the ice cubes that you put in it, and then the temperature of the room if you left it in there even longer. And so
exactly,
we had to use,
the horizontal asymptote would be room temperature. Brilliant.
Okay, so let's see here. Okay, so in this, let's work this one out. So going back to this, I have a variable in there now, right? So the first thing I'm gonna do is I'm gonna start the indices. I don't need the n up there, by the way. I just need 2. So I'm gonna start with, this actually looks pretty good. This is actually pretty good formatting. So the first thing I do is I stick 1 in there, right? Because n = 1. Got that, Drag?
Yeah. Yes.
Okay, so I start my indices at 1. So 1, then I go to the next one, plus, and I just increase my natural numbers. I'm just increasing, the ends basically stands for natural number. You're just increasing it each time. So I'm going to 2 now. So I put 2 in there. So my second one would be 2. So I add those together. I get a summation of 1 + 2, and I equals
3.
3. So if I change that top boundary, and I say, let's say we'll call it 4, what should this look like down here?
It should be 5.
Well, let's see. I put 1 in there, I get 1. I put 2 in there, I get 2. I put 3 in there, I get 3. I put 4 in there, I get 4. My summation is going to be 1 + 2.
Oh no, yeah, because it's a series. That's right. I keep
1 + 2 + 3 + 4.
Yeah.
That's
when you're calculating polynomials and genetics. I forget that there's a binomial expansion. When you're doing a binomial expansion, it's the same concept. I'm sorry, I couldn't think of what it was called.
Yeah, binomial expansions are kind of cool because now we're going to go off a tangent here, but if somebody can actually show this on their screen, maybe by drawing, can you draw this and show why when you have a binomial expansion? Let me start a new line here. So basically, what he's saying is, I hate those new lines shit. Okay, so binomial expansion is basically taking something like this and expanding it out. Okay, binomial of two variables in there. God damn, I really hate having to add all these new lines.
If I may, Steve, it's always best to start with Pascal's triangle to show the folks why it's true.
Pascal's triangles is obviously figure out the coefficients. But just by the expansion here, I don't really start off that way. I just say, look, if I want to expand this, I basically end up with saying this exact same thing. It's been a while since I've done this, so I'm doing this right, but okay, so that is exactly the saying that, correct? Everybody agree?
Yes.
I'm just taking the quantity A plus B and I'm squaring it so it's times itself. Okay.
Yes.
And then you just remember what you learned in high school called FOIL.
Yep.
First out and last. This is going back to grade school here. I haven't done this in ages.
A times A is A squared. A times B is AB. A times B is AB, and then B times B is B squared. So you have A squared plus AB. Yes, there you go. Plus B squared.
So you end up.
I got that right.
You end up with. Let me make new lines again. Damn it. There you go. So you're exactly right. So you end up with A times A is A squared. A times B is AB. Plus, actually, technically, not technically. It's not. It's just when you do it this way, it's BA, but it's the same thing. Let's see here. A squared. Then A times B, then B times A, and then B times B. Did I forget one? I did, didn't I?
I've done many of these.
There you go. There we go. Now, that's what it is. So AB and BA are the same thing, right? So that you just end up with 2AB. So my binomial expansion of A plus B squared is A squared plus 2AB plus B squared. Now, it's really interesting, though, if you do this and you look at it visually, if you take a line and you bisect that line, so half of it is A, the other half is B. When you square it, you actually end up with an actual square with all parts, you know, corresponding to boxes in that. Let me see if I can actually show you. Maybe as I make a visual representation.
Right, you have 2 squares and 2 rectangles, Steve. Is what you mean? It forms a big
two
square.
squares and 2 rectangles. So let me see if I can make this.
And by the way, can I say, Steve, we've kind of come full circle. This is so important because we need the binomial theorem to find derivatives of polynomials.
I don't know if I can draw on this particular thing, so let's see if I actually can. Now, I guess I have to use Paint. Let me see if I can. Maybe I'm just curious if I can do this in Paint. You guys want to know how binomial expansion is, like how cool it really is, how it works? I can actually show you this. I do remember this. Follow with me here, Eo. Okay, so I just gonna pick a line. Okay, oops. Nice. Oh, God damn it.
Hey, you know, if you want to draw actual straight line, yeah, there we go.
All right, so let's say I have a line here. Okay, now let's bisect it somewhere here. Let's say I just bisect it right here. Okay. Actually, you know what? I'm gonna do it this way. Let's bisect it here.
Sorry, Steve, you don't mean bisect, you just mean cut. Bisect means cut in 2 equal parts.
Yeah,
so just cut it.
Cut. Yeah, just cut. So text, we're going to call this A. Up here. I do not use Paint at all. Why is it not letting me put a text thing here? No, I don't want that. Get out of here. By the way, can you see this? Can you see the Paint? You can, right? Okay. So we call that A. Call this B. Okay, so this line segment A and this is line segment B. Okay. Now, when I'm squaring it, okay, I don't want to actually put that line in there. I just want to show you I'm bisecting it at that point here. So actually, let me erase that. Okay, so let's make this into a square.
Right, a square with side length A.
Yeah, this is too long, isn't it? Man, I haven't done this in a while.
Do you have a touchscreen, Steve? You can't do Paint
no.
with your
actually,
your
it should be like. Let's see here. This side on this side should actually be the exact same length, shouldn't it? I'm squaring the whole thing, so it should actually be the same as the top line. And same thing over here.
So, if I may, Steve, what you need to do is just label one part of it A on the top line, and the side line label it A, and then make your square of area A squared, and then you have the portion B.
Right.
I got it. So you have the rectangle AB. Yeah. Okay.
Yeah. So here is going to be A again. There's going to be B. Okay. There we go. That's a little bit better. Okay. So basically, when I have this line, I'm just squaring this line, right? So I'm taking a one-dimensional and I'm making it two-dimensional, right? Because that's people. They kind of don't understand conceptually what's happening when you're squaring something. You're actually, in this particular case, you're taking a one-dimensional thing and you're making it two-dimensional. Just like cubed, like x cubed is three-dimensional, right? Because you have length, width, and depth. So in this particular case, when I'm doing the squaring of the polynomial here, right? Remember, that's what we're trying to do. I end up with A times A, right? So this is A squared. Oops. Okay. I end up with A times B, right? Remember, this times this by this. It's basic geometry, right? I mean, take the one side and times it with the other. So I end up with B times A. Let me move this over a little bit. But B times A, and then I get B raised to the B. So when I add this all together, add up all these together, what do I get? I get A squared. God dang it. Plus, there we go. AB plus BA plus B squared, which is the same thing as A squared plus 2AB plus B squared, which is exactly what I had for the binomial expansion to begin with. Is that cool?
It's a cute little Punnett square-like thing you got going on there.
Yeah, it's very cool.
Yeah. And Steve, it's beautiful. The only thing is you can see that the bottom right corner should be a perfect square, and you kind of made it a rectangle. But the math is all right.
My graphics suck, but I mean,
it's fine.
Yeah, the concept's there that when you're doing the binomial expansion, the reason why AB squared is expanded to A squared plus 2AB plus B squared is exactly for this reason. You're actually making a two-dimensional representation of a one-dimensional line, ending up with A times B, B times A, and B times B. I think that's pretty cool.
Trinomial expansion, quadnomial. What would a fourth one be? X to the fourth.
Well, that gets a little more technical when you start doing x to the cubed and x to the fourth. We're going to get into that, but before we do, let's get into Pascal's thing real quick, because you mentioned Pascal's triangle.
Right, and that's why you need it, because, for example, it's x to the fourth plus 4x cubed plus 6x squared plus 4x to the x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. That's the expansion. If you want x plus 1 to the fourth.
Can you get? I haven't looked at Pascal's triangle in a while. Can you remind me what the things are in the order?
I think it starts at the top with 1.
Start with the 1 at the very top.
Okay.
And then the next. And then the
1,
1. Oh, shoot, I got
no, below that.
No,
I know.
And then underneath there's just 1. There's 2 boxes, but there's 1 in each box. And then you start adding.
And then you got to add them together, right? So 1, 1.
There you go.
There you go. So you got to go.
Yeah, new line.
So Midnight, what's 1 plus 1?
2.
There you go. See how it works? And you keep putting 1s on the outside?
I see.
Actually, it's going to be 1, 2, 1.
So that's 4.
And new line.
At the bottom.
And then you have 1, 3, 3, 1. I'm trying to do this in my head. Seriously, I have not done this in a while.
Hold on. Why is
check me as I go.
That's the beauty of writing out the triangle. You don't have to do it in your head. You just keep adding rows. So 3 plus 3 is 6. There you go. Right?
So 6.
So basically, Midnight, you're going to keep having 1s on the outside. You could think of them as kind of
no, it's 4.
Superfluous, I guess you could say. They're just out there to keep everything else in. So when you see, like, at the second row where those 2 1s, when those 2 1s add together, directly between them and below it is their sum. So you get the 2, and you go at the third line, you see 1, 2, 1. So that 1 on the left-hand side and that 2, they add together, they make that 3 directly below it. But if you go back to the third row, that 2 and that 1, those add together, the summation of that is 3. So that's why there's a 3 underneath that. And then there's 1s on the outsides to keep them in. And so you keep following that same scheme as you go down.
Am I getting this right? I'm pretty sure that it is, but I'm not.
No, 4 plus 6 is 10, Steve. You want a 10 there in the middle. 1, 5, 10, 10, 5, 1.
Wait, on my last one?
Yeah.
Okay, so 1, 5, 10.
We should all help Steve out. Just add the. Let's do it. 4 plus.
All of you are breaking
10,
up, kind
6
of.
Plus 4 plus 1 is 5.
Yeah, you guys are all breaking up a little bit for me, too. What should it be? It should be 1, 5, 10, 10, 5, 1.
5, 1. Right, but can everyone see that? You simply add the previous rows, the entries in the previous row.
Right. So the way this works is, look, I start with 1. And people are wondering what the hell it's used for. This is used for figuring out coefficients in expansions, okay?
So if I wanted to find out, like, let's say if I have a trait, like we use this in genetics. If you have, 3 children, and you want to figure out, you plan to have 3 children, and you want to figure out which one of them is going to have a particular trait, you can use this to determine what number of children out of those 3 will have this trait. And so that's why you use stuff like this, because you don't know whether it'll be 2 out of the 3, all 3, none, but those are all possibilities. So that the number of possibilities would be the coefficient.
Couldn't you
wait
use
one second.
this for something?
See this row right here, Midnight?
Yes.
See how it matches right here? The coefficient of this, do you know what the coefficient of this term is?
Where are you
If you don't
pointing?
see one, oh, you don't see my mouse. X squared. Okay. There's x squared plus 2x AB plus b squared above the triangle.
Yeah.
What's the coefficient of x squared?
1.
1. Okay, so it's called an implicit or implied coefficient. If you don't see a coefficient there, it's implied to be 1. So my coefficient there is 1. My coefficient for this term, AB, is 2. And my coefficient for b squared is 1, which is 1, 2, 1.
Okay. I can kind of, it's still, but I can kind of see, like if I do, I can always ask questions, like.
So if I do a trinomial expansion, if I do a plus b cubed, if I correct me if I'm wrong, I should end up with the coefficients 1, 3, 3, and 1. Correct?
Right. Let's do it together, Steve. So we have a cubed. Right.
Because this is for 0. This is for 1. This is for squared. This is for cubed. This is for the fourth.
Let's write it out, Steve. And this, by the way, the algebra is tedious. That's why we have to use Pascal's triangle. But what we really use is something called choose notation.
I hate this one. All right,
I know, but
we'll do it.
But so, Midnight, you still there?
Yes, I'm still here. Sorry.
Okay, so if I have a plus b to the third power, now, unfortunately, a lot of poor algebra students think that just equals a cubed plus b cubed, but there's a whole bunch of terms in the middle, right?
Yeah. Well, I mean, wouldn't you?
Okay.
But will you agree? A cubed shows up, right? A cubed will be the first term. Does everyone agree?
Well, hang on, before we do this, EO or somebody, can you find the actual? There's a coefficient expansion using K that it's kind of like the template to use. I wanted to show that first because that way we can match it up afterwards.
So it's the sum from n equals 0 to n equals so it's n choose k, the combinatorics, x to the n.
Let me get rid of all this. So
a to the n and b to the n minus k. Did you follow that?
No, one second.
Yeah,
let me get rid of all this. 1 sec. I got too many.
The way. Well, no, I was just gonna say that that the way I do cubes is I split them, so so there's a plus b times a squared. So so you do what you did above, and then you do a times a squared plus 2ab plus b squared, plus b times, like, you know what I mean, and then afterwards add them together. So at the top it would be a cubed plus 2a squared b plus ab squared. I mean, yeah, ab squared, and then at the bottom would be ab x squared a2. Yeah, am I going the right way?
I'm trying to find out the combinatorial way of expressing.
I have it, Steve. It's sigma.
Can you paste it to me? I gotta be able to type it in here.
I'll find it. Okay, hold on. I have it from memory, but I'll have to find it online to give it to you. Oh, I can use Paint too. No, I could use my notes. Just a second.
You know what? Yeah, how about I just screen share you for a second? You want to?
I'm on my phone, so I don't
show what it is. Oh, you're on your mobile.
Are we looking for a K expansion? You said.
Yeah, there's a expansion. See, I like using the expansion templates, the formats for it, because that way you kind of know.
The formula for binomial expansion.
Yeah, for trinomial.
Oh, trinomial. Okay. What you talking about?
Because I don't have it memorized. All right, but anyways,
I'm going to send it to you. Steve, I'll send it to you in your Facebook. Hold on. Can I send it to you?
Could you send it me in internal chat?
Oh, I think this is it. I want to make sure. Is this, let me present. Is that it?
Let me see here.
Expanding trinomials.
Yes.
Presents. Let's see here. No, that's what it comes out to be, but that's first of all that's a plus b plus c. We just want to do a plus b squared.
Or are you
But
looking for
that's not what I'm
Facebook
looking for as far as
third?
I'm looking. No, I'm looking for the actual. You know what I'm asking for, but I don't know what else to call it besides the actual binomial expansion using combinatorials?
Oh, I think I know what you're talking about. They use M and N's.
Yeah.
Okay. Hold on.
Okay. Yeah. Exactly.
Hold on. Screen. Okay, let me broadcast. You're looking for this.
Let me see here. Yes.
Except they use
No.
P's and
Well,
Q's
sort of. Yeah,
sometimes.
that is what it is. But when you expand it out, you get a nice long thing.
Okay. Yeah. So I got the what you
Steve,
call
I
it
sent
here.
it to you. I sent it to you in the side chat. I was just trying to paste it. I wrote it out. Do you see
Which side? Which side chat?
Any external. I see it. Here,
On the external?
Yeah, I got it. Oh fuck! I just had it. What the fuck happened to it? God damn it! Hold on. Oh, fuck. Yeah, it's an external chat. I just pulled it up.
I have the external chat. I see nothing there.
Well, no. I think
I'm not in my email chat. Yeah, I'm not logged in the I'm on my main account for the external chat, so I can't.
Okay, so let me.
I don't have an external chat for this.
Let me do this.
here's the image link. Hopefully,
Okay.
yeah, there we go.
All right.
That's not what I'm looking for.
That's not it.
Sure it is.
No.
That's
well. I mean, that's not how. But that's how it's written in a condensed form. I'm looking at the expanded. That's right, but I'm looking for the whole expanded thing out. Where you have like n minus one.
Sure. Hold on. I can write that out too. You want the?
I know what else to call it. I remember from my algebra books, obviously, in school, but I don't know what else to call it.
You want a to the n plus.
Oh, there we go. Yeah, exactly. A is your coefficient.
Yeah, that's fine. So you want a to the n plus n choose 1, a to the n minus 1 times b. Plus.
Hang on. Let me go back, dude. Slow down. I gotta go back here. Okay, so let me see if I can type this out. Present again. Okay, so let's see if I can present. Let me see if I can do this now. So okay, go ahead. So a
to the n.
To the n.
And really, the coefficient there should be n choose 0, but we omit it because n choose 0 is 1. You with me?
Yeah, fine.
Yeah. Plus n choose 1.
Plus n.
Choose 1. Do you know how to do that? You can just write capital C n comma 1 if you'd like, whatever works for you. There you go.
Okay.
Of a to the n minus 1.
Is it plus or just a to the
multiplied.
N? Yeah, a to the n minus 1
times.
Hang on, now I gotta put this in parentheses or it won't work. There we go, like that.
Yeah, beautiful. Times b to the 1.
Times b.
Little b, but sure. Yeah.
Okay, little b to the 1.
Now, I want everyone to pay attention. Add up the coefficients. Does everyone see that adds up to n? N minus 1 plus 1?
I'll need to broadcast them real quick.
Oh, I'm not presenting. I'm sorry.
Oh.
There you go.
Okay. Then the next one, Steve, is n choose 2.
Plus n choose 2.
A to the n minus 2.
A to the n minus 2.
Times what? Can anyone tell me? The exponents always had to sum up to n. So it would be b to the 2.
B to the b squared.
Yep, good.
And you just kind of...
Plus dot, dot, dot.
I know. So I'm just going to put that, dot, dot, dot. Oops, shit.
It has to be plus dot, dot, dot.
Yeah, plus dot, dot, dot. Okay. There we go. That's what I'm looking for.
Sure. Then let's finish it off. Plus.
Okay, wait a second. I can figure this out. I'm trying to remember this. Oh my goodness. It's right there inside my head. See, I know what I know.
N minus 1?
No, it's you want the format to be the same. You want the format to be the exact same as what the previous formats have been.
Yeah.
Oh, what is
n
it?
Choose
X.
n minus 1.
Oh.
1.
N choose
n minus 1.
N minus 1. There you go.
And Midnight said it. Good on you at Midnight. Good. Times
A. Yeah.
Times
A to the 1.
A to the 1.
1. A to the what? Can anyone tell me?
Minus
B to the n minus 1.
Plus b to the n minus 1.
Good. And then there's one last term. Can anyone tell me what it has to be?
1.
No,
No,
we had symmetry, right? We had A.
Can you explain this?
Wait, B to the n?
B to the n. Very good.
Yeah, here we go. Awesome. See?
By the way, what's the
coefficient? You can
coefficient?
just kind of figure out, you know, but yeah, B to the n.
Hold on. But
Yeah, I'm trying.
for everyone listening, the reason we don't include the coefficients is because n choose n is again 1, and A to the 0 is 1.
Yeah.
Everyone with me?
See, this is the actual formula that I was asking for, because this template, when you do these expansions like that and you have this, you can check your work. And like you said, there's symmetry, right?
What's the is that an L in the first thing?
No,
Like I'm trying to understand. Oh, that's a 1. Sorry, I'm trying to understand what.
Yeah, but the thing is, you don't have to actually show 1, but it's just easy, because the C1 it's choose to, you know. So.
Yeah, I was just trying to understand what the C is. Choose, like you choose a number, or
Yeah. So exactly, how many different ways can you choose one object from n of them? Take out your hand. Midnight. What's your name? Take out your hand. You have 5 fingers, right?
yes,
How many ways can you choose one finger?
5 ways.
There you go. How many ways can you choose 0 fingers? Just one way. You still with me?
Yes,
And how many ways can you choose 5 fingers?
5.
Good. And there's a formula. It's called the combinatorial formula. It's n factorial over r factorial times n minus r factorial. If you're interested, but we might be too far ahead of the field, Steve.
Yeah, no, I'm not. I don't want to get into
This is getting complex enough. As it is.
But you know, I just wanted this particular formula because this, you know, is how you have to. This works for everything.
Right,
You
but
know,
if
it gives you
anyone's
an
still
idea what's
listening,
going on.
see that triangle we drew? You don't have to do that factorial stuff. You can just find the relevant row of the triangle. Is everyone with me?
Right, but they're exactly the same way. I mean, the triangle is this. This is the triangle.
Yeah,
You know.
I'm learning so much today.
Okay, so basically, when we if you look at the binomial expansion we have, the a squared plus 2ab plus b squared. I hate the fact it doesn't show this when I'm typing it. I keep having to scroll
It goes
down.
on and on.
Get rid of this triangle. We don't need it. All right.
And you need a new line, Steve, after the B to the N. You should really do that new line.
There you go. So this is right here is really telling you this. It's basically saying, look, the n is my exponent, but it's also the value. For example, the a squared plus b squared. It's actually going to be this right here. This right here has to be equal to this, which is going to be 2 in this particular case.
I see.
So there we go.
It's still, but yeah.
Well, hang on. This value here, my n, right? Is this? Oh, you can't see where I'm putting my mouse, can you? The a plus b squared, right? That squared is your n. So in my binomial expansion, when I have a squared plus 2ab plus b squared, 2 is equal to that n. The coefficients here are going to be 1, 2, and 1, which is what we expected from the triangle, which was 1, 2, and 1.
Yeah, it's what happened? There we go.
See the 1, 2, and 1 in the triangle? This
Yep.
would be for squaring. If you square binomial expansion, you should end up with coefficients 1, 2, and 1. So here I have the coefficient 1a squared, coefficient 2ab, and the coefficient 1ba. It's just implicit. It's just implied there's a coefficient there of 1. So this checks your work. Does that make sense?
Yeah.
This is a Taylor series? What is this?
No. This is not Taylor series. The Taylor series is a Taylor series is a little bit different. Taylor series is when I had like the e to the x equals summation of x to the n by n factorial. Then you have to go back in. You have to put the values in there. And if you started at 0, it's called a McLaurin series. and you just expand it out. That's a little bit more technical. I'll do that video, but I'm not going to attempt to try to do it.
So, Drake, this
right
is a
now.
binomial expansion, but you do use the binomial expansion in the Taylor-Maclaurin
Yes.
series.
Yes.
Okay. Okay. Yeah. Because I remember doing binomial expansions. I don't. This notation is new to me. Well, somewhat. It may just be that the variables that we're using here are a bit different, but it does. Yeah, I do remember doing it for genetics.
So, Drake, we can do one of these, with Midnight, and it's great Steve is doing this, but if anyone wants to do these off air, we could do them, and we'll send donations to the Dragnot Silvis College Fund.
What about the G-Man College Fund?
Oh, God. G-Man is never going to college. Oh, God, I feel so mean.
All right, let's see if we can actually do the trinomial expansion here. Let's see if we can give it a shot here. Let's see if we can work it out. Okay, so let me get some new lines in here. I don't really don't want to erase anything here. Okay, new line. I want that format. Okay, here we go. All right, so how are we going to start this off, Midnight? If we're going to expand this out, because what we're actually saying here on this, let's make sure that you see what we're actually saying. So, squared or some cubed is equal to. Would you agree that this is equivalent? Is that the same thing?
Oh yes, that's basically what I was saying before.
Okay.
Like, you know what I mean?
So this is what sucks about this. If you're really going to do it the longhand way, or I think EO wants to do it, it takes time. You want to do it that way, EO?
No, in fact,
how do you want to do it? Do you want to do it the simple way then?
No, they're equivalent. That's the whole point. You can either use the triangle, you can use the combinatorial expansion. They're equivalent. But Midnight, here's the point. When we do derivatives, for example, I want to know the derivative of x to the 15th power. Even the brightest among us would take to do it. It would take 10 minutes. The whole point of doing this is so we have a quicker way of doing that. And what you'll learn is, okay, if y equals
also
x
the
to
power
17th,
rule. The power rule is the easiest thing.
But it's based on this. Hold on. The power rule is exactly based on all the work we've done today. The last part of this lecture.
Nice.
I just want to show you something real quick. The other way, okay, what you could do is you could actually do it this way, right? Then you start. Yep,
that's what I said before.
Right. I don't want to go ahead and finish this, but you understand how that you could do it this way? You can just take one quantity like this, right? You take these two quantities, you multiply these together, so you get this binomial expansion, and then you just do it a times b, a times 2 times a squared. Actually, you know what? I think we actually should do it this way first, and then show them the easiest way.
We can, but hold on. Yeah, we can, but I'll just note you have the formula up there. N equals 3, and hold on, son. We have how many ways can we? Then we have 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So go ahead, Steve, when you're ready.
All right, so let's expand this out. So we end up a squared. Walk me through this here while I'm doing this, because there's a lot of typing. So we're going to end up with
a cubed. A cubed is the first term.
Yeah, a cubed plus
2a squared b.
2a squared b plus ab squared plus
a squared b.
We're going to go to b. Well, b a squared. But okay, do you guys remember if I type it as a squared b? Do you guys care? It's easier if I do it.
Steve, just to let you know, you kind of messed up over here at the 2a. I'm sure you can fix it afterwards, but
where?
Where it says 2a to the power to like 2b.
Oh, I see. Yeah, you're right. It should be 2b squared.
Yeah.
There you go.
All right. Good catch. All right. So, this actually, like I said, it should be like b. A squared if you actually, but it's the same thing. So this is just easier if you do it this way. So b a squared is ab squared. So then I end up with man, I haven't done this since like college algebra, I think. So let's see. The next step would be 2ab squared, and then b times b squared is b cubed, and I put that. Is that right? Does that look right? No, something's not right here. I got too many squares in there.
I mean, Steve, if you put a,
you forgot
a
the
and b on top.
2a squared b, Steve. 2a squared b is
2a
the
squared.
term.
2a squared b squared. Where?
2a squared b.
2a squared. Which term?
The second term should be 2a squared b.
2a squared b.
What's going to happen is we're going to collect terms in the middle, and we're going to
There
get
we
these
go.
coefficients of 3.
Ah,
Good.
God damn it! It's not typing this way. 2a
A squared b.
Yeah, I know, but it's not letting me.
You could use Google Docs, but you're already
Anyway,
using this.
that's why it's having a problem. It's not. Yeah, I'm gonna have to do it that way.
Okay, good.
It's not letting me do implicit differentiation that easy.
Okay, hold on.
Yeah.
So then the next term should be.
But it should. But
AB
it should.
squared.
Hang on. But it should. I mean, I want it to look right.
No problem. So the fourth term, Steve, is a squared b, not ab squared. A squared b is the fourth term.
1, 2, 3. AB squared is
No,
what?
it's a squared b.
A squared b.
We're almost there.
All right. There we go. Yeah, this is messing me up because I know what it is in my head, but when I'm typing it out, it's not it's doing the
No, you
implicit multiplication,
didn't
right?
fix it. Hold, did you fix it yet? I don't see it.
No, I messed. Again, it's not. It's God. I hate this.
Oh.
Try this.
Okay, note to self: never use anything open office.
No, I'm sure there's a way around it. I just don't play with this that much to know the format. All right. So let's see here. A squared, 2a squared b
Plus ab squared.
plus ab squared. Okay, so it's ab squared. I can see the problem right now. So
Yeah, that's
this
the third term is ab squared.
right
And then the fourth term is a squared b.
is a squared b. I can fix that. You're right. I can see it. Look, how about that?
Good. Then the fifth term is 2ab squared. You got that? Good. Now
and then
notice
b cubed.
something beautiful happens in the middle. We can collect terms. Does everyone see that? We have 3a squared b in the middle and 3ab squared in the middle. Does everyone see that?
Yep. So let me make a new line here, and we're gonna go. We're gonna we have a cubed, and we're gonna collect the terms here. So we have let's see how many of the same terms here. 2ab squared. We have 3ab squared. Well, let's do the first term first. So 2a squared b. We have 3 of those, right? So
3 of those, yes.
a squared.
So 3a
I'm not
squared
really
b.
these, but Steve, you're confusing that.
Confusing the hell out of me. As I
hang
said,
on.
I've done.
Hang on. Let's work this out first, and then we're just collecting terms right now. That's all we're doing. So 3a squared
Son,
b,
I'm on air.
and then the next one ab squared. We've got
3 of those.
3 of those ab squared, and then we've got
Stay with us, Midnight. I promise it'll be worth the payoff.
oh, see, hang on.
Yep.
Yeah, hang on. This is a
3a squared b plus 3ab squared.
yeah. I don't like the way this does implicit multiplication.
Almost there, Steve.
All right. So what's the next term? All right. So what's the next one we're collecting?
3ab squared.
3ab squared.
Yeah, you got to get rid of that ab cubed in the middle.
I see it. Okay.
And make that
And-
3 at 2.
Oh, it's ab squared, right?
Yeah.
Yeah. Okay.
Okay. There we go. Now that is the correct answer, but now let's do it the easy way. Shall we, everybody?
Wait,
hang
that
on.
wasn't the easy way.
1, 3, 3, 1. Okay. Yeah. Let's check it real quick. So the coefficient here, the first coefficient is 1. The second coefficient is 3. The third coefficient is 3, and the fourth coefficient is 1. So I end up with 1, 3, 3, 1. And here on this triangle, 1, 3, 3, 1. So again, 1, 2, 1 was for squaring. You cube it, you should end up with 1, 3, 3, 1. And if this is square, if 1, 2, 1 is squared and 1, 3, 3, 1 is cubed, Midnight, what do you think would be for what would be the exponent if I have 1, 4, 6, 4, 1?
4, 6, and 4.
No, think about it. The exponent is squared, and I get 1, 2, 1 in the triangle, right, the top row. If the exponent is cubed, 3, and I get coefficients 1, 3, 3, and 1. If the next row is 1, 4, 6, 4, 1, what do you think that exponent is going to be? If this is the first one's 2, the second one's 3, what's the next one?
4.
4, right? And then so
Well,
the
I
next
was
one will
supposed
be,
to answer, but thank you, Dragnot, or whoever answered for me.
what's the next one? If I have the coefficients 1, 5, 10, 10, 5, and 1, what is my exponent? What is my n there?
5.
5, right? Yeah, exactly. Bingo. That's it. That's why there's a
There's a pattern, is what you're saying.
There's a consilience of all this stuff. This is why it's precept upon precept. If you learn the Pascal triangle first, and then you use this, this combinatorial thing that EO gave, it helps you understand what's actually happening when you're doing these binomial expansions and trinomial expansions. Right.
Well, I mean, the binomial expansion, I've done before. I've learned it before, so it wasn't too bad. The trinomial.
Well, let's do it the easiest way. Let's do it the easier way.
So sorry, Steve. I have to be pedantic again. These are all binomials. Trinomial expansion is 3 terms, and it's a lot more complicated.
Yeah,
These are all binomials.
I don't know why.
Right.
I keep calling them trinomials when I think it's cube, but it's not. A trinomial is using 3 variables.
Well, no, a trinomial is simply 3 terms, but all these expansions are binomials to begin with. You see that? It's always a plus b to something.
But if I have a plus b plus c cubed, isn't that a trinomial?
That's a trinomial, and that's a really hard one. It's orders of magnitude harder to do.
Yeah, I'm not going to attempt that one right now. All right, so let's do. Let me erase this. Let me just do the easier way to do this binomial. So, how do you want to do that, EO?
So let's start off with the exponent being n equals 3. That helps, right?
Okay, so we know n equals 3.
Good. Now the first thing is, so we know the first term right away is a cubed. Everyone still with me?
Okay, so the first one has to be a to the n, which is going to be a cubed, right?
Good. Now let's bring Midnight and Drag in.
Well, make sure that you understand this. You know why that is, Midnight? In this combinatorial expansion, a, the first term, right, is to the n, and n equals 3 because we're doing cube. So my first term in this expansion has to be a to the 3rd.
Yeah, I see.
Okay, all right.
Okay, everyone take out 3 fingers. How many ways can you choose 1 finger from those 3, everybody?
What is it? 3 to 3?
3 times?
3 times, good. So that's all the n choose 1 means. There's 3. A cubed plus 3 something. Everyone still with me?
Mm-hmm. So 3.
Good. Now 8, what's n minus 1? If n is 3, what's n minus 1?
2.
So 3a squared. Everyone still with me?
Squared.
And then b to the 1. Everyone still with me?
And then plus.
No, Steve. You did. Careful.
Steve,
I
hate this program.
It's this program. I don't like the way it does implicit. There you go.
And yeah, okay, good. Then now again, Drag, take your fingers out. Midnight, take your fingers out. And I don't mean anything dirty. You have 3 fingers. How many ways can you choose 2 fingers from 3?
You're minus 1.
So wait, what's it?
Take 3 fingers out. How many ways can you choose 2?
3. Because you have the 1 and 2, 2 and 3, and 1 and 3.
Everyone got that?
Does it make sense, Dragnot? Look at it. Hold your fingers up. You got 3 fingers, right? So I want to choose 3 different how many different ways I can do it? I can pick the first one and the second one. That's one way. I can pick the first one and the third one. That's the second way. Or I can pick the outer 2. That's the third way.
Is there a more intuitive way to remember that other than?
Fuck no! This shit gets complicated when you start.
No, it's all about choosing, Drag.
Yeah, but when you start doing statistics sucks, man. When you start getting into permutation and commutations, I'm sorry, it's just crap.
Oh, and let me make the connection. By the way, you guys are wondering, why is he making us pull out our fingers? Do you remember we did that last expansion with the algebra the hard way? Remember we had to collect terms? That's what we're doing there. We're collecting the terms when I ask you to choose. Do you guys get it now?
Right.
Okay.
Yeah.
Okay, so the third term, we have the coefficient 3. Okay, so it's going to be n minus 2, which is going to be a minus 3 minus 2 is 1, which is going to give us a, right?
Mm-hmm.
And then that's going to be b squared.
Yep.
Okay, and then the next term is just going to be a to the
b to the n.
B to the n. So n equals 3. So b to the n is equal to b 3.
B cubed. So do you guys see that? How much easier it was to use the formula?
So we didn't have to expand it all out. We just used the formula to figure out what it's supposed to be, and we could double check it by look at what is the coefficients 1, 3, 3, and 1. Going back to Pascal's triangle, 1, 3, 3, and 1, and then we check the exponents. The exponents is going to be n to the 3. The next one should be lower, right, by 1 because it's n minus 1, right? And then
you're doing fine. N minus 2.
N minus 1 again. So I have a to the cubed, a to the squared, a, and then a to the
1.
0 power is
1.
1. So I just end up with 1 b squared. So I don't show the 1, and I just end up with b squared. So each time I'm
Isn't that
reducing,
cute?
I'm basically reducing the exponent of x, or excuse me, of a 1 each time. So a to the cubed, a squared, a, and then a to the 0, which is just 1. And so you don't even show the a anymore because it's just 1, because then you end up with b cubed, right? And then what am I doing? What am I? So hang on one sec. So if I'm subtracting my 1 from my exponent every time midnight, what am I doing to my exponent on the b?
You're just putting it like that, aren't you? So it's 3. It would be b to the 3rd.
Well, no. Look at the formula. Look at the formula and work backwards. If I'm subtracting 1 from the exponent of a each time, can you see that I'm actually adding 1 to the exponent of b each time? Well, think about this. The first term would just be b to the 0, and b to the 0 is 1, so you don't show it. Okay. The second term is b to the 1, which is b. The third term is b to the squared, and the fourth term is b to the 3rd. So it actually is b1, or excuse me, b0, b1, b2, b3.
Yeah, I see. Because the b.
There's a
plus
symmetry
bn.
here.
Yeah, I know. I'm trying to get it, Steve. I'm not. I don't want to. I don't want to do any name calling. Like.
Let me see if I can type this. I don't like the way that the second term is. I wish it didn't have to put the parentheses around that to make that work. I mean, the only other way I could do it where I don't have to use parentheses is like this.
Name drop. I meant to say name drop, not name calling.
Yeah, like that. This is saying the same thing, but it loses kind of its form by doing it that way. So I don't like to do it that way. But anyways, you get the idea. Pretty cool.
Yeah, it is pretty. It definitely is pretty interesting.
So hey, Dragon, are you still there?
Okay, yeah, just get back. Yes.
All right.
Yeah, using the formula always seems to be a better way of doing it. And I mean, it's learning the long way. Just to give that basis is always a requirement. That's why I had to do that shit. Before we learned how to do derivatives, we had to do the fuck, you know what I'm talking about, the long way.
Yeah.
The definition of derivative, the binomial expansion. But hold on, Steve, can you put the triangle back for a second? For anyone in the audience who's had any calculus, did we lose the triangle?
Did Steve delete it? No, there we go.
Okay. Can you see the second entry in each row? Can you all see that? For example.
Yeah, 2, 3, 4, 5.
So for x squared, the derivative is 2x. For x cubed, the derivative is 3x cubed. I'm sorry, 3x squared. For the x to the 4th, the derivative is 4x cubed. For the x to the 5th, the derivative is 5x to the 4th. Can you guys see those numbers in Pascal's triangle?
And
that's exactly where it comes from.
Yeah,
that's where it comes from.
Let's actually show that real quick.
Well, I mean, I actually,
real quick.
Steve, I actually sent General Han Solo and also Dragnot and IO something that that General Han Solo seems to like it. I actually do talk about that in it. I don't know if Dragnot and EO looked at it.
I didn't get it, buddy.
I took a look at it.
I didn't get it, sorry.
It's a test for Mr. Intelligent Design. Want me to share it?
God.
Please, if I can teach Edgar, what I've learned,
I don't want to worry about Edgar right now.
Well, I mean, he's secondary.
Yeah. So, anyways, let's explain what he means. What you guys were meaning about the derivatives of x and 2x. So, if I have dy dx of x, it's basically saying the derivative of x, which is going to be equal to 1. Everybody gets that so far, right?
Yes. The derivative of x is always 1. The derivative of a constant is 0. Yeah. And so on. And then, so and that's it.
Let's take the derivative, and this is where Edgar gets confused. Okay, so let's take the derivative dy d over. I just broke my chair here. Dx, well, not broken, but my thing is loose. Dx works, so x squared equals. Fix this real quick. So you were talking about the power rule earlier, right?
Yep.
Okay, and the power rule basically states that you take the exponent, you bring it down to the coefficient, you subtract 1, right? So if I have to type the power rule, it's going to be let's see here, x
n
minus 1, nx raised to the n minus 1 and a new line. That's pretty much the power rule right there.
Yes.
Okay.
This mom is.
And this fine. We're gonna hopefully see where that is here in a second. So if I apply that power rule, and I'm gonna bring down the coefficient. So my coefficient here should be what? If I bring down the exponent, I'm sorry.
And I'm sorry, Steve. Just for anyone watching, your y's again are superfluous there. The
I know.
y is-
It's just habit. I know you don't have to have them, and it comes out the same. Especially, but I've done something with partial derivatives, and it comes out exactly the same. It's this habit of for me learning it as dy dx. But I know it's superfluous. But does it confuse people when I do that? Because it doesn't really make a difference.
With the notation?
Yeah, because the notation, the way I learned it is dy dx, although it's superfluous because
I learned both. I learned both
okay.
y prime and I learned dy dx, so that's fine.
Yeah, I mean, because when you take the partial derivative and it just goes to like 1 anyway, so it doesn't really matter. If I remember correctly.
As I said, I'm more used to the f, to the f prime of x rather than the dy dx. Although when I think about it, it's just basically the slope, which that's what the derivative is.
Right.
No, what I'm saying, no, it's just I'm not complaining about notation, but what he's written now is fine. What he's written now is what you'll see in the calc books.
Yeah. Although I've seen it both ways.
All right, so let's figure this out. So, if n is equal to 2 here, right? Because that's my exponent. What is my coefficient here?
1.
No.
Well, no, hold on. Hold on. Well, I mean, if
I'm
you're
taking the derivative of x squared.
Oh,
so
right.
So I'm moving to the coefficient, so I end up with 2, right? My coefficient.
Yeah, 2.
Then x, and then I'm subtracting 1 from the coefficient. So 2 minus 1 is
1.
1. So it would be that, which is exactly the same as saying what?
The derivative of x squared is 2x.
Because x to the first is the same as x, correct?
Yes.
Okay, so my derivative of x squared is equal to 2x. That you're already way ahead of the curve from Edgar.
Well, thank you.
Way ahead of the curve. I
suppose I could always send it to you on Twitter afterwards, but I'm way ahead of the curve.
But you got to understand, he claims to be a civil engineer, guys. He's claiming to be a freaking civil engineer, and he doesn't understand how to do a derivative.
Maybe in his dreams.
That's not reality. It's just not reality.
Nope.
There's no way in the world you can be a civil engineer and not know something like this.
This is not reality. Not reality. I forget from what movie that's from, but.
All right, so let's do x cubed, and then I want to show Drag something else real quick. If he's still,
nice.
Drag, you still here with us?
Yeah, I'm still here.
I want to go back to summations because I want to show you something cool. So use the power rule to figure out the derivative of x cubed there. Midnight.
The derivative of x cubed is 3x squared.
Right, but explain to people how you got that.
Okay. So I basically brought down the 3 and minus minus 1 from 3, so that makes it squared.
Okay. Now take the derivative of 3x squared, and what do you get?
Okay, so you bring down the 2, times it by 3, so you get 3, so you get 6x. And then you do 2 minus 1, which is 6x squared. I mean 6x. Sorry.
6x. Okay. Then you take the derivative of that. What's the derivative of that?
6. Well, hold on. Let me explain how I did that. Excuse me. Since it's 6x and the derivative of x is always 1, you do 6 times 1, and that.
Okay. What's the derivative of 6?
The derivative of 6 is 0 because because it's because it'll be, I think that's a vertical line. Yeah.
So this right here, this 3x squared, using your prime notation, what would you call this? We call this the first derivative, correct?
Yeah, the first derivative, the second, the third, and the fourth. The 0 is the last one.
Yeah. They call the fourth derivative the jerk.
I never knew that.
Yep. It's called the jerk. The fifth.
That's the third derivative.
No, what? No, you're right. The third derivative. The fourth is snap. The fifth is crackle. Six pop, right?
I never. Nobody
I'm
even
not
told
making
me.
this shit up. I'm not making
No,
this
I
up.
know. No,
Yeah,
nobody told me this
he's right,
nickname.
yeah.
It's literally jerk, snap, crackle, pop for the higher derivatives.
Jerk makes
Well-
sense, but if you think about it, a change in acceleration, that kind of makes sense. The others I lose
'cause
intuitive
it's
sense
a
for.
sudden change of acceleration. But you know where they get snap, crackle, pop from? They're just being dicks at that point.
Yeah, I think it's like we need a notation. So what's something that we can use and remember pretty easily? Oh well.
But yeah, I mean,
That's very good though. All right, very
Yeah.
good. So, but I really want to get back to the summations real quick if we can, because we have nobody watching, so fuck everybody.
oh
So-
wow, Steve,
so-
people just unsubscribed from me. You
Oh,
lost.
great debate community. Yes, you know we do this for our own edification. If people want to watch, great. If not, whatever. They don't even share this. If I had this on my main channel, you'd probably have still like 40 people watching. But
Yeah.
I didn't want this on my main.
But I've actually noticed people are more into drama than actually learning.
I know
Which is
you're right.
kind of sad.
We learned that ages ago. We're talking shit Tuesday.
So Drag, so we were talking about summations, right? So when you have this summation of n equals, let me new line, n equals 1, and up here, let's say n equals 1. We'll just call it 1. New line. Okay. So you got the hang of this, right? So this is equal to really 1, right?
So whatever n is, that's what it is.
Well,
Like,
it depends. If I have a 2, it's going to be equal to 3. If I have a 3 up there, it's going to be equal to 6. We're going to get into what we talked about earlier, the summation of 1/2 plus all that. I want to get into that. That's where it's kind of leading to at some point. But you understood this, right, Dragnot?
Yeah.
But there's also something really cool that you run into a lot, and people don't know what it is when they see it because it looks kind of it looks daunting, but it's not. I don't know how to use a symbol on here, so let me see if I can capital. It's called capital pi.
Capital pi.
Yeah, let me see if I can make the symbol for it.
Oh, you're trying to show them products, Steve? Finite
Yeah.
products and infinite products?
Yeah, but I don't know the symbol in math. Can you show him? Can you get him I don't know the symbol in this particular program. Well, actually, let me go to my symbols here. Maybe the symbols have it in the catalog. Here we go. Yep, right there. Capital pi. Okay, so sometimes you'll see something like this. We got a pi notation. Okay, it is almost exactly the same as summation, but with multiplication.
Oh,
So
I see.
so in this particular case, it's still 1, right? But if I change this to 2, instead of having 1 plus 2 equals 3, which I had with my summation, right? New line. Okay. With the sigma, it was 1 plus 2 plus 3. With the pi, all I'm doing is I'm changing that to times. So I end up with actually
it would be 2.
And that's how you do capital pi notation. People get so confused when dealing with capital pi notation because it looks so daunting. They don't.
Why is it called? Why is it called capital? I mean, I suppose it's called. They suppose it could be called that because it looks like.
It is pi.
Symbol.
It's the capital version symbol of the Greek pi.
Yeah, I know, but it's still 3.14.
No. It's just a symbol.
Ah, all right.
It has nothing to do with pi itself. It's just the symbol. The symbol is called pi.
And you won't see it unless you go into number theory.
Yeah, you won't. Well, that's not true. I mean, you see it on the internet. When you look at like math stuff, you'll see it out there. But a lot of people just see that kind of notation and go, "Oh, I don't want to deal with that." It's not that complicated.
Well, I mean, Steve, I'll tell you this right now. For me, it's the symbols that get them.
Yeah. Well, certain symbols get me. Like for example, what's called del operators. I confuse me, even though I understand what they are. They're dealing with three variables. But
if only mathematicians would choose simpler symbols. Oh well.
No, it's not. The symbols don't confuse it. You have to remember what the symbols represent, what they're telling you to do. Like in this particular symbol, the capital pi, it's telling you take the product of n and then add it to the next value of n, or excuse me, times by the next value. So if n equals 1, right, times, and then equals 2 times 2. So if I have n equals up here on the top, I have 3, right? what's the next term that's going to be here? Times 3, right?
Yeah.
Okay,
So it
and
will be 6.
be 6, correct?
Yep.
So the capital Pi notation for my indices of n equals 1 to 3 is 1 times 2 times 3 equals 6. There you go.
Yep.
Pretty cool.
Yeah, I mean it is pretty cool. I've actually taking a course Coursera on Calc 1.
I'm no Ronnie, but I kind of did have this at one time.
I mean, it should be interesting.
You know what, Steve? It's funny. I was just thinking n factorial could benefit from that notation.
Oh, okay. You want to do? We're just doing all kinds of math stuff. Let's have fun here. So, what is n factorial? Midnight. What do you think? And if I say something like, let me make a new line here. New line. If I say 2 factorial.
If I remember correctly, you times like you do 1 times 2, which is 2. Say if you have 3, 3 factorial, you have 1 times 2 times 3, which is 6. If you have 4 factorials, it's 1 times 2 times 3 times 4, which is 12. Hold on, 1 times 2. No, hold on. 24. 1 times 2 times 3 is 6. That times 4 is 24.
Oh, 1 times 2 is 2. 2 times 3 is 6, and 6 times 4 is 28.
6 times 4 is 24.
12, 18, 24. I'm sorry, you're right.
I was like,
yeah.
I mean, I have the teacher's
Well, the other one
life.
would be work backwards. 4 times 3 is 12. 12 times 2 is 24. Times 1. Oh, I got to make new lines. Shoot. I hate this.
I wonder if Mr. ID will ever run into this video.
I doubt it. All right, so there you go. So he's exactly right. This is how you do factorials, right? So 1 factorial is equal to, let's do the first one first. 1 factorial would just be equal to
1. Oh! You should
okay,
talking about the 0.
Now, well, yeah. Now we're gonna get really confusing here. Greg, are you there?
I know what.
Here we go.
Oh well, never mind. You already put it in equals that.
So if 1 factorial is equal to 1, and 2 factorial is equal to 2, and 3 factorial is equal to 6, and 4 factorial is equal to 21, what do you think 0 factorial is?
I would say 0.
But you'd be wrong, motherfucker! Wrong, bitch!
What?
It's actually 1.
It's also equal to 1. Oh, okay. So
It's defined. Hold on. For convenience, it's defined to be 1.
Yeah, and if anybody asks you why, I always just tell them because it is literally defined that way, because God wanted it so. There's really no other reason.
Careful, don't go down that road.
They just define it to be that way because it works out. And the reason I wanted to point this out, because when I get into Taylor series, this is something you've got to remember.
Yeah.
Because you have 0 factorial in a Taylor series.
Yeah. So
you gotta know it's 1.
Yeah. So if you see that in Taylor factorial, it's a denominator. Don't be scared. You're not dividing by 0.
Right. Exactly. Because have you done Taylor series?
I've looked into them a little bit.
Yeah, so you're right. Because in the Taylor series, you're in your first term, and you end up with 0 factorial. It's just 1. Because it's been a while since I've done Taylor series, but
sorry to be a pedantic, Pete. Just by convention, though, they go the other way. They run down from the highest number. So 4 factorial, they usually write it 4 times 3 times 2 times 1.
Convention is to go highest to lowest. Yes, you're right. Yes. We're gonna tell you pedantic Pete.
I won't be invited back.
Right.
It's the same thing.
But I mean, it's good to learn proper format, though.
Yeah.
That's actually how you would actually write it if you, but you write it this way.
I'm going to have to take off, folks. My wife is getting hungry.
All right.
Sorry, Steve. I have to go too.
Yeah, I'm done with this video. Did you pick anything up from it, Drag, or anything? Did anybody get anything useful out of it? I mean, I have done this stuff for 25 freaking years, and I didn't expect to get into factorials or summations. So I'm just pulling that completely out of my ass from my head that I've had, before. But it's not that hard. But
You
you guys get something out of it?
You've done it before. Yeah, well, I mean, yeah, I took something out of it. You know, good stuff.
Yeah. Well, I mean, but you got to remember, the Clown Car Posse thinks that I haven't even been to fucking high school, right? I mean, they don't understand. I did graduate.
Wait. Are you?
You have to have mathematics.
Yo, Steve, are they confusing you for Kent Hovind?
I don't know. They don't understand the math involved with nuclear physics is not freaking easy. You got to know a little bit about math, you know.
A little, more like a lot.
So, anyways, the next time we're going to do another proof. Like I said, I'll try to get into Taylor's series. And there's something else I wanted to do a video on that showed drag, something interesting, but I totally forgot what it was. I'll have to think about it afterwards. But anyways, guys, thanks for watching. Yeah, this was a little bit longer than expected. My 4 viewers that hung in there, which is basically me, Drag Midnight, and Odeon, I think, are the only 4 watching right now. You know, thanks for that. Tomorrow, I'll do another video probably, and then General is going to actually have a series of mathematical things where he's going to start off with either algebra or pre-calculus and kind of do more of a lecture type series for people wanting to learn calculus, wanting to learn pre-calc, and starting from a little bit of the basics. And I think that's going to be fun. It's going to be interesting. I don't mind taking a refresher on it. This stuff, you forget the stuff you don't use it, like that combinatorial formula. I could probably, if I had to really sit down and figure it out, I probably could have. But I knew what I was going with it, but I just haven't seen it for a long time. But anyways, guys, thanks for watching. And you know what? I'm not going to give anybody the last word because this isn't my particular channel. So take care, guys.